Hi everybody. Let's go back to cook YouTube again. This one I'm going to talk about modern physics. Let's make it start to be your series 1. Okay. And then what have here is the start from the photoelectric effect and then move on to something like laser and X-ray, and then talking about light spectrum, and there's some laws come to play around with, for example, like Planck radiation law, Wiener displacement law. Okay, let's start with the photoelectric effect. Many of you are probably familiar with this effect already, so it just refresh you about their effect, how this one happen, and what kind of equations associate with the photoelectric effect. Well, if you take a look at the material, usually material they have like atoms, and they all are neutral. So that means you have a equal positive charge equal to or negative charge. And you take a look at the atom, and you have nucleus, right? And then you have the rings. That's you have electron move around here, and then inside the nucleus you have proton that have the positive charge, include the neutron with no charge. The photoelectric effect occur when you shine the light, and you know that usually when the light shining on the surface of any kind of materials is come with the energy, and energy can be calculated from E equal to h nu, or nu, or sometimes they use F. Nu actually is the frequency of the light, and you know that for the light you have many different lambda, and you can also calculate for F equal to c over lambda, because you're talking about the light, so the speed of the light is actually c, or 10 to the 8 meter per second. So this is actually you can calculate the photon energy. So in the real life, when you shine the light on the surface of materials, electron is in the material is going to be excited. This means have the freedom to move, and then what happened? They have the photoelectric effect. You have equation. The energy that you are supplied to the system, or in this case is material, is actually equal to the work function. Okay, this means, or sometimes they call like the energy, the minimum energy required for electron, to be free, and this is what we call the work function. And if you have more than enough energy from the light shining on the surface of material, part of the energy going to go to for work function, and the rest is going to give you the kinetic energy of electron can move around. So you have equation. The energy of the photon actually equal to the kinetic energy of electron plus the work function. Okay, and the kinetic energy of electrons using the classical physics is equal to 1/2 mv max square, where h is the Planck constant. If in unit of joule second is equal to 6.62 10 to negative 34, and you can also find h in the term of electron volt and then second. Simply divide 6.62 10 to negative 34 by the electron charge, which is what, 1.6, right? 10 to negative 19 coulomb. And also you can find the relation between electron volt and joule, right? Or let's say you want to change the unit of energy from electron volt to be joule. You simply multiply, just take this term out, simply make it equal to 1.6 10 to negative 19, and you're going to end up with the unit of the energy is joule. Okay, so you already know that when you shine the light with the energy of the photon h nu is going to be part of it going to give to the work function, and the rest you're going to give to electron moving around with the kinetic energy equal to 1/2 mv max square. For example here, so this is actually if I shine the light with the photon energy to be 1.14 electron volt. Okay, so don't get confused about the photon energy. The photon energy you can calculate from E equal to h nu, which is equal to hc over lambda, in case they give you lambda instead of frequency. For the silicon films, that means you make the silicon, which is the semiconductor. This can make the silicon to be a better conductor by shining the light, and that's what we call photoconductivity. Sometimes you deal with the p-type and n-type, right, in a semiconductor to change the electrical property of silicon, or change the electrical property of semiconductor. But in this case, you use the photo, so that's why we call like photoconductivity, to change electrical property of the semiconductor. So far in this case, what are we looking for? You're looking for lambda. You can simply calculate. You give energy to be 1.14 electron volt, and then your lambda equal to hc over E, energy of the photon, which is 1.14 electron volt, and C is equal to 3.010 to the 8 meter per second. Many of students confused about a unit, but in this case you know that your lambda have to come out to be in the unit of meter, right? So you have meter right here, and when you use the energy in the unit of electron volt, you also need to use the Planck constant in the unit of electron volt second, which is equal to 4.136 10 to negative 15. And same thing as here, as I mentioned before. This is h Planck constant is in unit of joule second, and if you want to find the Planck constant in the unit of electron volt second, you simply divide this number by the electron charge, which is the 1.6 10 to negative 19, right? And that's you end up with lambda equal to 1.09 micrometer, and this is the infrared spectrum. Okay, so now what about this one here? If you apply the reverse or stopping potential equal to 1.25, ask you to find the Vmax. How do you find the Vmax of electron that free from the material here? Well, you take a look at this one here. When you're talking about voltage, it in the unit of volt, but you are multiplying by E. Okay, don't get confused. You can simply, for this one, is the voltage 1.25 volt, and if you're looking for the energy in the unit of electron volt, you simply say that this is become 1.25 electron volt. Okay, you change from the voltage to the energy. So 1.25 is still there. You don't have to do anything, but the unit is going to be electron volt. For in the case if you want the unit of the energy to be joule, you simply multiply 1.25 by electron charge, which is 1.6 10 to negative 19, right? And it gives you the unit of joule. See, that's why I have right here, and it's ended up to be 2.00 10 to negative 19 joule. This is your Kmax, or your maximum kinetic energy of electron. So from the relation Kmax equal to 1 over 2 me or Vmax square of electron, you can find Vmax. Rearrange the equation right here and plug in number, because you have Kmax and me. Now you take a look at the equation right here. V, you want the unit to be a meter per second, right? This is the SI unit. And then our ME, you know that this is in the unit of kilogram, right? 9.11 10 to negative 31. But what about Kmax? What the unit you're going to use? Well, all about here, you're working on an SI unit because you want the velocity to be the unit of meter per second. So this one you need the unit to be joule. So that's why you multiply the electron charge 1.6 10 to negative 19 to 1.25 electron volt. And finally you have Vmax equal to 6.63 10 to the 5th meter per second. Okay. Okay, so let's move on. Alright, this is interesting example here. Well, they give you the plot between V0 and F, and you already know that from the previous page. You apply the energy of the photon, and part of the energy is going to give to the work function, right? And then plus the rest that is going to be the kinetic energy of electron that's moving with the velocity v. So this has become very simple photoelectric effect equation. When V0 is stopping potential, what does mean stopping potential? Right? I did not mention, in the previous page. But what the stopping potential is mean is that when you have an electron free from the surface of any kind of material, because the you have absorbed the photon energy. So when you electron moving, that means you have the current moving. So it's, you know that in the opposite direction of the electron motion, right? So what you need to do is that you don't want the current flowing, so you need to bias with the voltage on the opposite direction of the voltage. That's why we call this is V0 is the stopping voltage or stopping potential. So from the plot here, I ask you to find phi, which is the work function, and the Planck constant. How can you do that? Alright, just like I told you, the photon energy is going to be equal to the wave function plus the kinetic energy of electron. So this is nothing much more than simple math. When you have the relation between V0 and the frequency here, what you can do is you need to rearrange the equation to make a V0 to be y-axis and F to be your x-axis. So when you rearrange the equation, it looks like this one here. This is simply become y, right? And your F is simply become x. So you know obviously that this is y equal to mx plus c, and your slope become h over e. Right? When you know, or you already know the e, right? The electron charge, right? 1.6 10 to negative 19. And now from the plot, this will give you the slope. That's why I have right here. I pick up, you know, the triangle here. Oops, not very good. Sorry. I pick up the triangle here. Right. So this is 90 degree, and then this has become theta, or tan theta. Sorry. Tan theta is actually the slope of the line, right? And what is the slope of the line? The slope of the line is simply equal to tan theta, which is equal or delta V0 divided by what? Delta F, correct? That's why I have for delta Y or delta V0 here, I have 3, because this is 3 minus 1 divided by what? Delta F. So I have 1.0 here, and I start from here is 0, so I have 1 minus 0, so I have 4, and then don't forget to multiply by 10 to 15 hertz, right? So I have 4 over 10 to the 15 volt second. And now you want to find the Planck constant. Okay, it's the same. It's going to be 2 units. One is electron volt second, and the other one is joule second. For h in the unit of electron volt per second, you simply, you know, like move for e, you know, to the right, and it will give you, you seem to be for e, but actually e is going to be in front of voltage, so you don't have to do anything with 4 10 to negative 15. So your h still become 4 to 10 to negative 15 electron volt second. But if you want in the unit of joule, you simply multiply, you know, 4.410 to negative 15 by electron charge, which is 1.6 10 to negative 19, and you end up with h equal to 6.4 10 to negative 13 joule second. Okay, so that's how you find h. Next, what about phi? Well, this is the equation here, the same thing as y equal to mx plus c, right? So what is your c? C, actually, if you have the plot, c is the intersection, you know, on the y-axis. And you look at this one, it intercepts y-axis at the negative 1. So this one give you c, and equal to y-intercept, which is negative 1 volt. And for your phi, you have E right here. Phi over E equal to negative 1 volt, and you move E up here, so you have the unit of phi become 1 electron volt. You don't have to do anything with 1. And then if you want to change the unit of phi in the unit of joule, you simply multiply 1 by 1.6 10 to the negative 19, right? So this is become you have to play around with unit. Okay, don't get confused. Otherwise, you will get a wrong number. Now take a look at the radio station in case is the broadcast with the frequency 89.3 megahertz and radiate power to be is the 43.0 kilowatt. Ask you to find the magnitude momentum of each photon. Okay. Well, I just pick up this one, which I'll prove. You can go back to quantum physics, and maybe I have chance I explain about it later on. P related to the energy of the photon, simply divide the energy by the speed of light. Okay, so E equal to hf or h nu. Sometimes they use different symbol here. So you plug in h. P you want in the unit of SI unit, so h need to be in the unit of joule second. So that's equal to 6.626 10 to negative 34, and then you multiply by the frequency that's already given here, 89.3 megahertz. Mega is equal to 10 to the 6, and you divide it by the speed of light. So you have the momentum to be 1.9697, sorry, 10 to negative 13. And then they also ask you more about the number of photons emitted per second. Okay, number of photons emitted per second. Okay, let's start with this one. You have radiated power to be 43.0 kilowatt. This is the total energy that radiated from the radio station. What you need to do is that you simply divide the radiated power or the total power by the photon energy. You have to know that one photon has how much is energy. So take a look. One photon energy is actually equal to h f, correct? So this is h in the unit of joule second, and this is the frequency. So you know that one photon have energy 5.92 10 to negative 26 joule. They give you in the term of power. Power simply is become the energy per second, correct? So the unit still become joule per second. That's why they ask you how many photons emitted per second. So you take a look at the unit here. You need to divide 43.0 kilowatt by the photon energy, or this one here. So that's why I have 43.0 10 to third joule second divided by the photon energy, which is the 5.92 10 to negative 26 joule. So you end up with 7.26 10 to 29 photons per second. This is how you find number of photons emitted per second when the radiated power is given. So this is our relation of the energy E equal to hf, and before this we talk about the photoelectric effect. Now let's move on to atomic line spectra and energy levels. Okay, so we already finished the photoelectric effect. Okay, let's take a look at atomic line spectra at energy levels. What you see here is they have two energy level. That's have EF and EI, which is F subscript F is represent a final and I is initial. Usually when electron absorb some type energy, even in terms of a photon, is going to be excited to the higher energy level. So for example, if the photon have the energy HF, electron is going to have energy to be the EI plus EF, and it's going to be at the final electron level, the final energy level. And usually electron doesn't prefer to stay at the higher level, so it's going to be try to come back at the initial energy level, which is at the lower energy, and it will release the energy in the form of the photon or in the form of light, and that's become the basic of our laser and or yes in this case is laser. Let's take a look at an example here. If a krypton atom emits a photon of orange light, which have the wavelength to be 606 nanometer, then it will release the energy of the photon. You can calculate from E equal to hc over lambda, and you have lambda to be 606 nanometer, so you end up with the energy to be 3.28 10 to negative 19 joule, or you can calculate in the term of unit of electron volt. Simply divide by 1.6 10 to negative 19 coulomb or electron charge. This gives you a 2.05 electron volt. Now you take a look at the hydrogen spectrum. It's going to be different wavelength of photon or wavelength of light or wavelength of spectrum. So you have like H alpha, H beta, H gamma, H delta, and H infinity. When the wavelength is increasing from the left to the right, and H alpha is the visible line or red light, H beta is blue-green, and H gamma, H delta, and H infinity. And I have the number of n to be infinity, n equal to 6, just to show you later on, what does this mean when you have n here. We already have our equation for wavelength calculation. This is the Balmer series. They have a 1 over lambda equal to r multiplied by 1 over 2 square minus 1 over n square. When r is the Rydberg constant, is equal to 1.097 10 to the 7 per meter. And of course, lambdas have to end up with the unit of meter. So this one has no unit or unitless. So r have to be unit of 1 over meter. Okay, just keep that in mind. And since this is 1 over 2 square minus 1 over n square, and start from 3, 4, 5, because the number here lambda cannot be a negative number, so n has to be greater than 2. So that's why I start from 3, 4, 5. And this n represent, you can find lambda here from Balmer series. You plug in the number, that's why I have H alpha n equal to 3. H beta is n equal to 4, you're going to end up with lambda. You can work this one out by yourself. For example, if n equal to infinity here, this term drop, right? So you have end up with 4 over r become lambda, and you plug in r equal to 1.097 10 to the 7. You end up with lambda equal to 364.6 nanometer. That's why you have lambda here at n equal to infinity. And from our Balmer series equation, 1 over lambda equal to r multiplied by 1 over 2 square minus 1 over n square, you can also find the photon energy of each light spectrum. Simply use this equation, E equal to hc over lambda, when your lambda is equal to this one here, and you can separate term to be your final energy and initial energy, EI, or En equal to negative HCr over n square. This is the initial energy of our hydrogen atom. And for example, you want to find the energy level of the hydrogen atom. You can take a look at this one here. When you put E equal to E2, E3, and it start from, you're not talking about a ground state here. Actually, I have n equal to 1, right? It's become the ground state. Simply become negative 13.60 electron volt. And when n equal to 2, you end up with negative 3.40 electron volt. And this is n equal to 3. It's going to be getting closer and closer for energy level of hydrogen atom. Please keep in mind that why the energy of our hydrogen atom is become like this, because when you use the Balmer series, you can find your energy level. E simply become hc over lambda when your lambda is represented by this equation. There also are other equation for lambda in different types of series. You have Lyman, you have Paschen, you have Brackett, you have P-Fund series, and they all start with the different n. This is Lyman series. This is 1, this is 3, this is 4, this is 5. So for different type of series, n is going to start from different number. So this 1 and it has to be less than 1. Oh, sorry, it's greater than 1. And here n has to be greater than 3. And for Lyman series, it's going to cover ultraviolet, because you have the wider energy band gap here, so it's cover ultraviolet, and the rest just only cover infrared. So you look at the atom here, you have nucleus or inside, and you have n equal to 1, n equal to 2, n equal to 3, n equal to 4, and so on. Take a look at the energy band diagram for this is the ground level here for Lyman series, and start from 2. Okay, what I have here is I try to explain. Um, this is, for example, you have the E ground level and you have E1 level at the energy 1.0 electron volt and E2 at energy level 3.0 electron volt. As I mentioned earlier, electron try to come back to the ground level that have a lower energy. So the possibility that it's going to come back to the ground state can be E2 to E1, E2 to ground, and E1 to ground. So what I show here is calculate to find the different frequency, or you can also find a different wavelength at each energy transfer or energy transition. And since the energy level in the unit of electron volt, you need to use your H in the unit of electron volt second as well. Okay, so this is just show you other equation for lambda using different series. Now let's take a look at the Bohr model. It's the associated with the hydrogen atom. From the picture, this is like the nucleus here. You have the proton here, because hydrogen atom, you have one proton, right, and one electron move around the nucleus, and you have the separation between proton and electron to be Rn. Simply just to be more clear, it look like this one. Electron moving in a circular motion with velocity Vn, and you have the center force to be your F. By using the Coulomb's law, you know that the force is going to be 1 over 4 pi epsilon 0 Q1 multiplied by Q2 divided by Rn square. I mean the separation between electron and proton, or the separation between two charges, and that's going to be equal to the center force, which is equal to mv square over r. This is the classical physics or classical mechanics. You rearrange the term, you can get Rn equal to epsilon 0 n square h square over pi me square, same as Vn. Vn is going to be 1 over epsilon e square over 2nh. For your Rn, you get Rn directly from this equation. Okay, this is the electric force or Coulomb force, but this one is the center force. And you get Vn from the relation mv Rn equal to nh over 2 pi, when n is the principal quantum number. And this is on the left hand of the equation is simply angular momentum. And when you're talking about linear momentum, simply multiply the mass by the velocity. But for angular momentum, you have the relation mvr equal to nh bar, when h bar equal to h over 2 pi, if you still remember. And that's how you get Vn, like this here. Now you take a look at the Rn equation. If you separate n square, just pick up the factor here. You can calculate by yourself, because you only do epsilon 0, which is what, 8.85 10 to the negative 12, and h, Planck constant, m is the electron mass, e is the electron charge. So Rn is equal to n square is 0. So it's not a big surprise when n is the greater. You have R become bigger and bigger, right? And if you want to calculate for A0, this is we call ball radius, equal to epsilon h square over pi me square. You put it in epsilon 0, and this is h in the unit of Joule second, because you want A0 in the unit of meter. And m is simply your electron mass, E is the electron charge. You end up with A0 to be 0.529 angstrom. Okay. Now take a look at the energy levels of our electron. E total in any kind of situation is going to be the kinetic energy plus the potential energy at each energy level. Okay. So let's start with the kinetic energy first. You know that is equal to 1 over 2 mvn square, and you already have Vn in the previous page that we did calculate before. On the page number 4, you have Vn right here, E square over epsilon 2 nh. Okay, E square over epsilon 2 nh, and this become Kn, and also Un is equal to negative 1 over 4 pi epsilon 0 E square over Rn. And then you plug in Rn that you calculate, earlier. You end up Un to be this term. This is also from the Coulomb force, right? You're familiar with the potential energy. What is that? When you have an electric charge, two of them. So it's become 1 over pi 4 pi epsilon 0 and E over R, right? But this is for electron, so you have to multiply to be the energy of electron. That's why you have E square over there. And then you add them up, you end up with E total to be negative 1 over epsilon 0 square me square over 8n square pi h square. This has become the total energy of electron at any energy level specified by n, or the principal quantum number. Okay, take a look at example here. You talk about H atom in the first excited level. Okay, we have to make agreement. The first excited level, you have the ground state here, and if you put this one to be E1, the first excited energy level have to be at energy level E2. Okay, that's why I have N2 here, become first excited state, and N equal to 1 is become the ground state. You already have the equation for kinetic energy, and you already have equation for the potential energy of electron at energy level n. Okay, so you calculate this is Kn simply become 13.6 electron volt per n square, and Un become negative 27.0 electron volt over n square, and you find E total is become negative 13.6 electron volt over n squared. You're probably familiar with this number already. Now for the first excited state, that means n equal to 2. You plug in n equal to 2, you end up with a different number. This is the kinetic energy, this is the potential energy, and this is the E total. You add this one, you add them up, you have a negative 3.4 electron volt. That means you start energy level at the ground state at the negative 13.6 electron volt, and the first excited state is going to be at the energy level of negative 3.4 electron volt. And when electron want to come back to the ground state, it will release the photon, or in the term of light, you have the different delta E, or the different energy become negative 3.0 minus 13.6, and this gives you 10.2 electron volt. And if you want to find the wavelength of the photon, or the wavelength of the light, you can calculate from lambda equal to hc over E, or E equal to hc over lambda. So you end up with lambda equal to 1.22 10 to negative 7 meter, or 0.1 micrometer. Okay, next one we take a look at the laser, and then we will get into X-ray. Okay, let's take a look at the laser. Actually, is the generate the beam of highly coherent. This means the same phase and close to monochromatic light. Okay, what I have here in the picture, you have the energy graph rail here, and you have N1 is the excited energy level. As you know that when you have some atoms here, or electron, when it absorbs photon energy, it's going to be excited to the higher energy level, and it's become a star. And you also have you're probably familiar with the spontaneous emission. What does it mean? It means that the higher energy of a shard or electron is going to try to come back at the lower energy level, so it's going to emit the photon, or in the term of light. And also you have stimulated emission. This means when this guy release energy and come back to the lower energy at the ground state, it also come back and hit another charge and release also the photon, and this photon is going to be absorbed by another atom or electron. So that's why you increase the number of photons, and that photon is going to give the energy to another sharp particles and release more. So it seems to be just like you have much more photon, or you have the more condensed light. So let's take a look. The laser. The laser stands for light amplification by stimulated emission of radiation. So it's come from this one, stimulated emission of radiation. And atom is the ground level absorb a photon with the energy E equal to hf. Now take a look at the Maxwell-Boltzmann distribution function. Ni equal to a exponential negative ei over kt, when EI is the initial energy state, or the starting energy level. And Ni is become number of atoms in the state with the energy EI, and you already knew K, Boltzmann constant, T, absolute temperature, and A is determined by the total number of atoms in the gas, and that's one had to be the unit of number atom. And if you take a look at the different energy level, Ex and Eg, G is represent our ground state, and Ex represent our excited energy level. You can find the ratio of the number of atoms in excited state and the number of atoms in the ground state, by this relation. So simply become exponential negative, the difference of the excited energy and the ground state energy over kT. So this one in the excited state, you have with the ratio of the ground state, you need this one to be more than 1, correct? So that's why you need to increase number of atoms in the excited state. Okay, and that's we call, or if you have more atoms, number of atoms in the excited state than the number of atoms in the ground state, we call that as the population inversion. So how to get the population inversion, or how to get the number of atoms in the excited state more than the number of atoms in the ground state? One technique is we call helium neon laser. This is helium, this is neon energy band diagram. It had the state of 1s and they have the state of 2s. For neon, you have the 4s, you have 5s, you have 4p, you have 3p. For helium, when electron absorb their energy, is going to go to the higher energy level. In this case, it's the excited energy level. So approximately about at the 2s energy level is about 20.61 electron volt. And when it try to go down to the ground state to have lower energy level, okay, it's gonna collision with the neon at the ground state here. So that's why I have the step number 2. And then when neon collide with the helium, it's going to absorb some energy and excited to be at energy level 20.66 electron volt, or at the energy level 5s. And then after that is going to after that, finally helium is go back to the ground state, and this is very crucial. Okay, that's how you get the population inversion. Now the neon atom itself try to go to the lower energy level. So when it's come down here, it will release another photon energy, and it's going to be absorbed by another atoms. And that's why you have more, in general, you have more and more atom at the excited state, because you have photons that give away your energy to atoms at the lower energy level to be at a higher energy level. Okay, and this is the typical laser tube. You have a cathode and you have the anode. You supply the voltage here to make electron or the shard move from the left to the right, and then when you have the light, is going to reflect it by mirror, both from the left from the right, and it's make uh, the light of the laser more condensed, or stronger. Okay, so that's in general how the laser work. As for X-ray and scattering, it's actually to be is the mechanism is going to be opposite of the laser. When you have an electron here is coming in, it's going to be accelerated by the potential difference. So you have the negative charge here, you have positive, so electron gonna accelerate it toward the right and hit the mirror target and release the X-ray. And in general, the wavelength of X-ray is going to be in the range of 0.001 nanometer to 1 nanometer. And when you accelerate it, that you give the energy to electron. Simply, this is the EVAC equal to SC over lambda min. That's how you calculate for lambda. For example, if you have VAC equal to 10k volt, you can find your lambda min simply divide SC over SC by EVAC. And lambda min is something about 0.1 to 4 nanometer. Okay, so that's the rough idea about how X-ray and laser work. I'm not going to get into details, just we can talk about it, because this is, if you want to see a lot of details, you have to go to the X-ray and laser topics. Now it's talking about Compton scattering. What does it mean, Compton scattering? Compton scattering is simply when you have the input source, let's say lambda, you can change your wavelength of the light or the photon to be your new lambda. That's what our Compton scattering means. Okay, that's why you have equation here. If you take a look at the equation, delta lambda, that means the wavelength change is going to be h over mc multiplied by 1 minus cosine phi, when phi is the angle that's the X-ray deviated to from the original direction. And this situation you cannot explain by using classical physics, but you need to use the quantum physics to explain how this one happened. And you take a look at this one. You have the lambda of the photon is coming in, and when they hit like electron, they have electron here, it's going to deviate it to with the angle phi and give you a new wavelength and the new momentum. And you can find P total. Simply look at the vector here. This is you have the X-rays coming in, and this is the deviated path, and you can find P total. Let's take a look at example. If you have lambda equal to 0.2124 nanometer, you can find phi for delta lambda equal to 0.1%. This is simply work on math. When you have delta lambda equal to 0.1%, that means it's going to be equal 1.24 10 to a negative 12, because your lambda is the 0.124 and 10% of 0.124 is equal to 124 10 to a negative 12 meter. And your take a look at equation here. You have h over mc equal to this one, and then multiply by 1 minus cosine phi, and you plug in delta lambda is equal to 1 to 4 10 to negative 12. Is I missing something here? Oh, this is lambda, delta lambda here. You plug in the number here, and you end up with the cosine phi equal to 0.4889 degree. Okay, so this is the Compton scattering. Again, you can change your wavelength of the photon to be the new wavelength of the photon by using Compton scattering. The next one is continuous spectra, talking about a hot matter or about a hot object, as you well known as the black body. Okay. How does this work? It's said that hot matter in a condensed state or in the solid state or liquid state is going to give a continuous radiation out of the black body. So when you have a lambda of electromagnetic radiation, come to the black body, the black body will absorb the electromagnetic radiation and release the continuous spectrum radiation, and thus come into the Stefan Boltzmann's law, represented by I equal to sigma T to the fourth, when T is the absolute temperature in the unit of Kelvin. Sigma is constant, okay, and then I is the intensity in the unit of energy per second per area, or when the energy per second is simply the power, so it's become the power per area. And since the intensity is the lambda dependent, that means it's dependent on lambda. So when you want to find the total intensity, you need to do the integration from 0 to infinity of I lambda d lambda. Please keep in mind that I here and I here are different, because I here is the intensity, but I here is the spectral emittent in the unit of the power per unit area per meter. That's why you are multiplied by lambda. It's in the unit of meter. So meter cancel out. You have left is the power per unit area, which is the unit of intensity. So I here and I here are not the same. Also having displacement law, lambda max multiplied by the absolute temperature always constant. The Planck radiation laws, you have the new equation I lambda equal to 2 pi hc square over lambda square exponential hc over lambda kt minus 1. To find lambda max, you need to differentiate I lambda by lambda, correct? This is your I lambda, and this is your lambda. It's going to give the curve like this, give you the maximum point. So you want to find the lambda max, that gives you the maximum I lambda. You need to use the calculus. So it's a little bit complicated because you need to differentiate I lambda with respect to lambda, which you have lambda here and here. You can work this one out by yourself. Let's give you lambda max equal to Sc over 4.965 T, when T is the absolute temperature. Let's take a look at the sample here. The sun temperature at the surface is about 5800 Kelvin. So from the equation you can find lambda max. It's about 500 nanometer, which is become the visible spectrum. That's why you can see here the sunshine, right? And the intensity of the radiation equal to sigma t to the fourth, when your sigma is come 5.67 10 to the negative 8, and t is the 5800 Kelvin to the fourth. This gives you 64.2 megawatt per meter square, or per unit area. Okay, so that's all about continuous spectra. Okay, so this one is just refresh, and then we talk more in the next YouTube.